Welcome to homework.
Okay, we've got a few molecules and we're asked if it would be possible to have cis-trans isomers of those molecules. So we're going to start with A. And for there to be cis-trans isomerism, it simply means that we need to be able to have a two possible versions of the molecule in which our substituents are, in one case, on the same side of the ring, and in the other case, on opposite sides of the ring. That is, if we draw a wedge to this hydroxyl group, right, that's above the ring. And if we replace this bond to bromine with a dash, that bromine would be below the ring, right? And that this would be categorically different from this would be the trans isomer, by the way. This would be a different molecule or have different connectivity, or same connectivity, but it would be a categorically different molecule. You couldn't like put both of them. If you put both of them in your hand and shook them up and pulled them back apart, you could tell which one was which, right? You can tell the difference between cis and trans. And so if we tried to look at the cis version of this molecule, where we put the OH and the bromine on the same side of the molecule of the ring, in this case, they're both coming up at us, that's fundamentally different than the trans isomer, right? We've got both substituents on the same side, both substituents on opposite sides, and without breaking bonds, we can't make the one on the right look like the one on the left. They're different molecules. Let's contrast that with B. Okay, we've got OH here, and we've got CH3 here. So maybe you're thinking, hey, well, let's just put a wedge to OH, okay, and a dash to CH3. Is this trans? They're on opposite sides of the ring. I have OH above the ring and methyl below the ring. Well, the problem is that if you rotate this molecule, right, it's the same molecule, you could flip it around, and all of a sudden you've got CH3 on top and OH on the bottom. And it's the same exact molecule. It just looks different. We're just holding it at a different angle, right? So these are the same molecule. They're not isomers in any way, right? The other problem is if, like, okay, we thought maybe this could be the trans isomer because they're on opposite sides of the ring. But what would the cis isomer look like, right? You can't have a trans isomer without having a cis isomer. But that would mean, okay, let's put a wedge to the OH and a wedge to the methyl. You can't have two wedges, right? They'd be overlapping. That's impossible. So in this case, yeah, you can have two wedges because they're on different carbons. It's totally fine. The cis isomer is just, it's facing up on this carbon, the OH and the bromine on this carbon is facing up. That's not possible if both the substituents are on the same carbon. Okay. So it's not possible for B. B cannot exist as cis-trans isomers. And just to show that C can, it's obviously the answer is B, but one could imagine OH here. And we draw this other OH on the same side of the ring. Okay, that looks like cis. And we just flip one of them to being a dash under the ring. And there we go. That's the trans isomer. So, and you can't get from one to the other just by flipping it around, like in your hand. You'd have to pull the oxygen off and then flip it over and reattach it. Remember, because there's a hydrogen here, implicit and implied hydrogen, right? You can't just slide the OH up so it looks like the the other one, it's a fundamentally different molecule.